Hello there. This lecture I'd like to go, this is part 4. I'm going to look into the prediction of shear angle. Okay, we're going to look at the prediction of shear angle. So this is a this is a physical model. Okay, and it's predictive. So the first one we're going to look at is a merchant shear angle model. Okay, so it's merchant shear angle model. So in merchant shear angle model, he derived a relationship where the shear angle pi is equal to pi over 4 minus by beta over 2 plus by alpha over 2. Okay, so this is his relationship. This is his model that has a relationship with a friction angle, a rake phase, to predict the shear angle. Okay, so it's to predict the shear angle. So let's look at the assumption that he has made first. Let's look at assumptions. So before we use any models, you need to look at what they assume. So the thing that they assume is the 2 is infinitely sharp. That's the first thing. The material is isotropic, same direction in every angle. The deformation only occurs in a finite plane. And the cutting process is at steady state. So what do they mean by steady state? So if you have a time function, right, and this is time, and this is the shear angle, what it means is, so you will tend to have this trend that's going on. So over here, right, anything on the left hand side, this is known as transient, because the shear angle is not constant, and the shear angle will affect the deformed chip thickness big T. Whereas on this side is steady state. So we assume that the shear angle don't change so much. Okay. So these are some of his assumptions, and furthermore, he also assumed, the assumption that he make is that the friction angle which is beta, right, will remain constant. Right, beta will remain constant, and it's not affected by process parameter. And the other assumption that he make is the shear angle. Okay, and these two assumptions are important. I'm going to put star down here. And the other assumption he make is that the shear angle pi, okay, will orientate itself itself such that fp, okay, fp will be at its minimum. Okay, so this is what I'm saying. So i.e. this is the minimum, okay, minimum work, okay, minimum work assumption, okay, minimum work assumption. So the last two assumptions is very important, okay. So now the first thing we do is we have to relate, okay, so the first thing we do is we have to relate, okay, so the process we have to relate fp to fs. And why fs is because fs is affected, okay, why fs? Because note, right, fs orientation is controlled by the shear angle, okay. So I'm going to draw a merchant circle, not the full circle, but this is the diagram that you need to derive merchant circle. So 2, 4, 6, okay, over here. So we know that the direction from here to here, right, this is our R, and then we are also aware that from this is our FP, okay, so two key forces are FP, and the other force that's important for merchant's model is Fs, okay. So we have your FP, and then if we have your Fs. So how do we relate Fp to Fs? Is through what? The resultant force, okay. And then if the associate angle, we know that this is controlled by the shear angle. We know that this angle over here is beta minus alpha. I'm going to draw two more lines so you can visualize it better. So this is your FQ, right, and the next one there is your NS. Okay, so you have to write out, okay, the first thing you have to write out is you have to write out FP, okay. So we have to, so FP and FS shares the same resultant force, which is your R, okay. So over here you can write down that FP, right, FP is equal to R cos beta minus alpha. This is your equation number 1, and Fs is equal to R, right, R cos pi plus by beta minus alpha. This is equation number 2, okay. So from equation number 1, you can have the relationship where R is equal to Fp secant beta minus alpha. So this will become your equation 1a, okay. So you substitute your 1a into equation number 2. So you have Fs is equal to Fp, right? Fp secant beta minus alpha cos pi plus by beta minus alpha. Okay, so this is your equation number 3. So the next thing we have is we need to find the shear stress acting on the shear plane. Okay, we're going to find shear stress acting. So the shear stress that we got is tau s is equal to Fs over by As. Okay, so this is your equation number 4, and where As, like we have done this, where As is the area of the shear plane, and As is equal to T omega over sine pi. Okay, we have seen this before. So therefore, equation number 4 will become tau s is equal to Fs, which is Fp secant beta minus alpha cos pi plus by beta minus alpha, and then divide by T omega, and then this is our sine pi. Okay, so we're going to apply minimum work theory. Where Fp, right, will be at its minimum. So if you look at one of the assumptions that we make, right, the orientation of pi will be such that Fp will be at its minimum. So therefore, when that's the case, so therefore Fp is equal to tau s T omega divided by Fp secant beta minus alpha cos pi plus by beta minus alpha, and then sine pi. Okay, so when you get to here, we make another, we assume tau s as constant. Okay, that's what merchant assume. So for Fp to be at its minimum, the entire term at the denominator, this term have to be at its what? Maximum. Sorry, you have to get rid of Fp there. This term has to be at its maximum. So we know that this value over here, this is constant, because beta will not change. Based on process parameter. That was the assumption. Right, so the assumption over there is from here. Okay, friction angle beta remain constant and it's not affected by process parameter. So therefore the denominator has to be at its maximum. So we are going to let, okay, so from here we are going to let y okay, which is a term in the denominator, is equal to cos pi plus by beta minus alpha and sine by the shear angle. The whole thing is equal to 0. So if you look at this function, right, if you look at this function, so what we have over here is we have a magnitude y, and then we have to have pi. So it's cos and sine, so you're going to have a wave looking like this. So maximum y will occur at this point. So at this point is what we call dy over d pi is equal to 0. Okay. So we now know this function y is going to be a function of the shear angle, because that's the only changing term. So it's equal to cos pi plus by beta minus alpha sine pi. Then we're going to do the derivative dy by d pi. So this will be equal to cos pi plus by beta minus alpha cos pi plus by minus, this will be minus, because cos to sine, when differentiate sine pi plus by beta minus alpha, then have sine pi. The whole thing will be equal to what? 0. So from here you equate both of them. So cos pi plus by beta minus alpha cos pi is equal to sine pi plus by beta minus alpha sine pi. Okay, so from here we know that you can get cotangent pi will be equal to tangent pi plus by beta minus alpha. To transfer this to tangent is equal to pi over 2 minus by the shear angle. So this is equal to tangent pi plus by beta minus alpha. Get rid of the tangent, you have pi over 2 minus by the shear angle. So this is equal to pi plus by beta minus alpha. So you move things around. So you have 2 pi is equal to pi over 2 minus beta plus by alpha. So your shear angle relationship is pi is equal to the pi minus over 4 minus beta over 2 plus by alpha over 2. So this is the shear angle relationship derived from Merchant's theory. Okay. Well, you realize that it's purely geometry based. Okay, just looking at the geometry. Okay, so I'm going to stop here. When I come back, we're going to do the other model by Lee and Schaeffer. Thank you.